Hi everyone. In this video I'll be going over 3.6, the chain rule. It's a very important rule as far as taking derivatives goes. It'll allow us to take derivatives of more complex functions in general. And here's how it goes. So if you have a function, capital F, and you want to take its derivative, so here's the function capital F, but capital F is not just any function, it's a composite function. So you have F composed with g of x. So you have a function in a function creating yet another function, and you want its derivative. So to find capital F prime, what you do is you actually take the derivative of the outer function, still composing that outer function as it was, but then we need to multiply by the derivative of the inner function. Okay, so this is the Leibniz notation way of saying that same thing. I actually prefer this presentation. It tends to make a little more sense to me. I'll do a good amount of these examples just so we can get some repetitions. So example 8. So here's a function capital F, and we want to find its derivative. Okay, so within this chain rule, you're going to be using potentially the other rules as well. So it's not like this rule is separate from the power rule or product rule or quotient rule. It includes those rules, so we'll use them as they come up. So looking here to find capital F prime of x, what is the outer function? So maybe I'll rewrite f first. So if you have 4x plus 1, and then the square root would be the same as the positive 1/2 power. So the outer function is that square root function, right? Inside of that square root function, we have a linear function. So the outer function, in other words, this lowercase f, would be this square root in this case. So the first thing I'm going to do to take this function's derivative is to take the square root function's derivative. So I'm kind of thinking of it as just like if it were the square root of x, or x to the 1/2, right? Same thing. So I'll multiply down by 1/2. The rule says to still compose with the original function. So it's still composed with this 4x plus 1. To take the derivative fully of the outer function, I need to reduce the power by 1. So I'll have negative 1/2. It was a 1/2, reduced by 1, you have negative 1/2. But then I need to multiply, and I'll just kind of mix notations now apparently. But now I need to multiply by the derivative of that innermost function, which was the 4x plus 1. So let me highlight a couple things here maybe. So this piece right here is what I just did. So this first piece, that's the derivative of the outermost function. That's this part. And then what it says is to multiply by the derivative of that inner function, and that's what I'm setting up here. I haven't actually differentiated yet, but I'm just setting that up just to break it down into steps. Okay, so actually differentiating, so I'll have capital F prime of x equals 1/2 multiplied by 4x plus 1 to the negative 1/2. And then times, so the derivative of 4x plus 1 would just be 4. So times 4, and I'll simplify this. So 4 times 1/2 is 2. The negative power, I can rewrite this in the denominator. So I'll leave this as actually 2 over the square root of 4x plus 1. So that would be the derivative. I'll go ahead and do the next one. as well. So for this one, we have this power function, right? This something to the 63rd power that is really my outermost function. So I'm going to take the derivative first by using the power rule, since the power function is my outer function. Inside of that power function, I have this quadratic. So to find g prime of t, in other words, to differentiate this, I first differentiate the outermost function, which is this something to the 63rd power. So I'll multiply down by 63, compose as it was, reduce by 1, and then I need to multiply, in this case my variable's t, so I'll write ddt of 1 minus t plus 2t squared. So I still need to do the derivative of this, but I'm just breaking it up into parts. So g prime t, so taking this derivative, I'll have -1 plus 4t. So 63 is 1 minus t plus 2t squared to the 62nd, and then times -1 plus 4t. I'll just leave it that way. I'll do this one too. So h prime of theta is what we're looking for. So h prime of theta. So the outermost function in this case is this trig function sine. Inside of sine is this polynomial in terms of theta. Okay, so the first thing I'm going to do is take the derivative of the outermost function, the sine. The derivative of sine is cosine, so I'll say cosine of theta cubed, but then I need to multiply by dd theta of theta cubed. So h prime of theta will be cosine of theta cubed times 3 theta squared. And we would typically probably write that as 3 theta squared cosine of theta cubed. All right, some chain rule. They definitely get more complicated than that. I'm going to go on to, I'm leaving this one open for you guys, but I'm going to go on to, here's a new derivative formula for an exponential function. So this is saying if you want the derivative of this exponential, where we have a base b raised to the x power, then it's exactly itself, but then times the ln of b. And this is not the chain rule. This is just the formula for the derivative of the exponential function base b. What if you wanted not just, so I'll say and, let me add to this. So what if you wanted d dx of b to the g of x? You know, what if it weren't just x up here? What if it were a whole nother function? So this would be exactly itself, b to the g of x, times ln of b, right? That's what this formula is saying. But then by the chain rule, which is the section we're talking about now, I would actually need to multiply by g prime of x. I'm going to write that again over here. So if you want the derivative of some exponential to some function, then yeah, it is just itself times the ln of b. That's true, as this is saying. But then in this more specific case, you'd also need to appreciate the chain rule and multiply by g prime of x. So this is a more specific formula that involves the chain rule. So this is like exponential plus chain rule, if you will. All right, so example 9, let's try this one. So I want f prime of t. So what this is saying is to find the derivative of an exponential, well, you always get exactly itself, right? So I'll have 9, 3 root t times the ln of 9. But then, according to this more specific version of this derivative formula, I need to multiply by d dt of 3 root t, right? I still need to find this part. This is the chain rule piece, and that's why I included that over here. So I still need to take this derivative. By the way, this is the exact same as 9, 3 root t times ln of 9 times d dt of 3t to the 1/2. And I'll often think of these roots as powers. It just helps the derivative if we do that. So f prime of t in full now. So I'll write everything else that we had. And then this derivative. So 3/2 t to the negative 1/2. So simplifying all this stuff, it looks like, let's see, I'll write it as 3 times 9 raised to the 3 root t times ln of 9 over, there'll be a 2 root t from this piece. Okay, on to part 2. This one is a little more complicated, right? You have tangent of secant, but then inside of secant you have a sine. So you have a composite within a composite, in other words. So to do this one, we're going to have to really emphasize the chain rule a lot. So, all right, f prime of x. So the first thing I'll do is I'll take the derivative of the outermost function. Derivative of tangent is secant squared. There's a formula on a page somewhere before this one. So secant squared, and then I still have of secant of sine of x. Okay, but then I need to multiply by d dx based on the chain rule of the derivative of this inner function, which is secant of sine of x. So I still need to do this part. I'm going to break this down into steps like this. So this piece is done, right? And now I'm on to this piece. So interestingly, with this piece, we have yet again another chain rule. So we have the chain rule happening within the chain rule. So the derivative of secant is what I want to do first, because that's the outside function. And then I'm going to multiply by the derivative of the innermost function. So this would be secant squared of secant sine of x times the derivative of secant is secant tangent. So I'll write secant of sine of x tangent of sine of x, but then I need to multiply by d dx of the inner function, which I haven't differentiated yet, which is sine. So I still need to do that last derivative. So this would equal secant squared of secant of sine of x times secant sine of x tangent sine of x, and then finally derivative of sine is cosine. Okay, so I'm not going to write secant cubed, right? I can't do that because they have different arguments, right? This is secant of sine. This is secant squared of secant of sine. Okay, so this would be it. This is our derivative, f prime of x. That's what we were finding. All right, let's try a tangent line. So on page 45, this will be the last one we do. I'm not going to pull up Desmos, but I do encourage you to do that whenever it will help you. I need to correct something here though. So if you plug in pi, you do not get 0, and we need that this point is on this curve. So what I need is actually to correct this point. If you plug in, so if you find y when x is pi, that would equal cosine of pi. Cosine of pi is -1. So the y value that I get is actually cosine of -1. So the point should be the point pi and cosine of -1. And you need to be in radians. So actually it should be this point. So we'll do the same thing. It says find an equation of the tangent line to this curve, but at this point. All right, this point actually is not on the curve. That was a mistake. So for the tangent line, we need the slope and a point. This is our point, so we just need the slope. The derivative is the slope to the curve at any point you want, right? Derivative slope, slope derivative. That's a connection I'm really encouraging. So we need to find y prime to find the slope. Y prime, we have cosine of x. This is a composite function. We need the chain rule to differentiate here. So the first thing I need to do is take the derivative of the outermost function, which is cosine. The derivative of cosine is negative sine. So I'll have negative sine of cosine of x, but then I need to multiply by d dx of cosine of x. I'm writing a lot of steps, right? As you get quicker, you don't need to do all these steps. So now what do we have? Derivative of cosine again is negative sine. So y prime equals negative sine of cosine of x times negative sine of x, right? Again, I'm not going to multiply sine times sine and write sine squared because this is sine of x and this is sine of cosine of x, and those are different arguments. But I will go ahead and cancel these negatives. Negative times a negative is a positive. So y prime would be sine of cosine of x times sine of x. We weren't just looking for the derivative, right? We want the tangent line. So what I now need to do is evaluate the derivative specifically at the x that we care about, right? This derivative is access to the slope of any tangent line that we care about. We specifically are fixated on the x equals pi tangent line, okay? So a piece of notation for that, y prime evaluated at x equals pi. Okay, sometimes we use this notation when we don't have function notation to plug into. So sine of cosine of pi times sine of pi. Let's see what this is. Cosine of pi is -1. So this is sine of -1 times 0. So this is 0. So the slope of that tangent line at this location that we care about is actually 0. Sorry about that. So this is our slope. Our slope is 0. And this is our point. So I'll go ahead and write this equation now. So we'd have y minus cosine of -1 equals 0 times x minus pi. The 0 times x minus pi, that all just vanishes. So I have y minus cosine of -1 equals 0. And I'll go ahead and add over cosine of -1. So it'd be this horizontal line. It'd be this tangent line at that point. All right, talk to you all next time.